Hello everyone, my name is Marina. I'm a PhD candidate at Purdue University, and I'm going to be presenting my project entitled Accelerating CO2 Uptake in Cement Pastes through Titanium Dioxide Nanomodification. And before I start, I want to acknowledge the co-authors of this publication, Dr. Carlos Moro, Dr. Vito Francioso, Hussam El-Jali, and Dr. Miriam Belay. So to start, this is the outline of my presentation. I will start with an introduction and motivation, then materials and methods, and then results and discussion, and some final conclusions. So for the introduction, we all know that climate change is one of the major issues that we're facing nowadays in our society. It relates to the changes in weather and temperatures due to human activity, and it causes many issues such as the increase in temperatures, extreme weather events, pollution that of course causes a lot of health issues, fires, droughts, and even rising sea levels. So one of the main contributors to this issue is the emission of greenhouse gases, mainly CO2. And even though we've known this for a while now, and we've been trying to tackle this issue, we've seen that CO2 emissions globally are still increasing every year. In fact, last year, 2023, was recorded as the hottest year ever. So who is to blame for these emissions? There's a lot of industries involved, of course, but the construction and building sector is a big one, as you all know. Concrete is the most used construction material in the world because it's a very good material in many aspects. However, it does have a big environmental impact. Just to give you an estimate, for the production of cement, this material is responsible for 8% of the total CO2 emissions emitted every year. So because of the wide use of concrete, because it's a very used material around the world, we do have an opportunity here to make concrete part of the solution instead of part of the problem. So one of the approaches that we may take is to sequester CO2 into our material, into our concrete, and that is known as carbonation in cement-based materials. And carbonation is basically the process by which calcium hydroxide and other hydration products of cement react with CO2 in the air to produce calcium carbonates. So this is great, however, it has the drawback that it's a very slow process. It takes a lot of decades to complete itself, but there are ways to accelerate it. So an approach to accelerate this problem is to cure our material with CO2. So this has proven not only to enhance the CO2 uptake, but also to improve certain properties such as the compressive strength. And also there's a different approach that's been more recent, and is to add nanotitanium dioxide particles into the mixture. So this has been shown to enhance mechanical properties, produce some new properties such as photocatalysis, and also enhance durability. But in a recent publication that we did, one of our previous studies, we saw that added titanium dioxide nanoparticles can actually double up the amount of CO2 that we can capture in the air. However, the effect of these nanoparticles and the effect of CO2 concentration in the CO2 uptake rate, or how fast we uptake that CO2, is still not known. Therefore, the objective of this particular study is to understand the mechanisms that govern these changes in the CO2 uptake rate produced by the nanomodification and CO2 concentrations. So for the materials and methods that we used in this study, we use ordinary Portland cement type 1, water, and 2 different concentrations of titanium dioxide nanoparticles, 0 and 1%. And with that, we produced cement paste prisms of a water to cement ratio of 0.55. And these are the mixtures, the ones with titanium dioxide and the ones with titanium dioxide. For the curing procedure, we did 28 days of curing in water, and after that we did a pre-curing cycle to kind of prepare the samples for the exposure of CO2. And in order to assess this effect of the titanium dioxide nanomodification in the CO2 uptake of the samples, we did an accelerated CO2 exposure of 8 hours. And that CO2 exposure consisted of placing 3 samples of the same type inside of a sealed chamber along with a CO2 sensor to monitor the changes in CO2. Then we enter CO2 inside of the chamber through one of the valves, making sure the other valve is open so that the air can be pushed out of the chamber. And we stopped at the desired CO2 concentration. And for this, we tested 3 different initial concentrations, and those were 25% CO2, 50% CO2, and 100% CO2. After that, we tested for 8 consecutive 1-hour cycles, so a total of 8 hours of CO2 exposure, and we weighted the samples before and after. And in order to estimate the CO2 uptake and uptake rate, we did 2 main methods. So first, we used the sensor that we placed inside, and we call this method CO2 sensor monitoring. So we basically took the concentration at the beginning and at the end of each cycle and calculated the difference of that. And with the other method, we used the weight method, which basically accounts for the increasing weight due to carbonation because of this creation of calcium carbonates. And now looking at the results, these are the results for the first method, the CO2 sensor monitoring. You have here the CO2 concentration in the y-axis and the time in the x-axis. And we have each color represents each different initial concentration. So on the top, in blue, we have the samples that were exposed to 100% CO2 concentration. In the middle, in green, the samples exposed to 50%, and in red, the samples exposed to 25%. And then we have the samples that were nanomodified, which are the gray ones, and the samples that were not nanomodified, which are the black ones. And as you can see here, as time goes by, we're actually seeing a decrease in the CO2 uptake rate, which is something that is expected due to carbonation slowing down over time. And in this graph on the right, you can see the cumulative CO2 absorbed per each cycle. And again, each color represents the initial CO2 concentration. So red is 25%, green is 50%, and blue is 100% CO2. And the solid lines represent the samples that were not nanomodified, and the dashed lines represent the samples that were nanomodified. And as you can see, we do have an enhancement on the CO2 uptake rate when we increase the CO2 concentration and when we add the titanium dioxide nanoparticles. However, we see that the contribution of these nanoparticles is much higher when we're exposing these samples to lower CO2 concentrations compared to the samples that were exposed to higher CO2 concentrations. And we can see that in the graph on the right. As you can see, the difference between the red lines and the green lines is much higher than the difference between the blue lines. And we believe that is because the nanomodification of the sample does accelerate this process a lot more. So if you're exposing it to a higher concentration, you're actually accelerating this process a lot in the first cycles, therefore reducing the porosity much faster, preventing further carbonation in the next cycles. And these are the results with the other method, with the weight method. We have the CO2 uptake in the y-axis and the CO2 concentration in the x-axis. Then empty bars represent the samples that were not nanomodified, and the filled bars represent the samples that were nanomodified. And as you can see, in all cases, titanium dioxide nanomodification did increase CO2 uptake. However, we did see a difference with the previous method, and that's only for the case of the sample exposed to 100% CO2, not nanomodified. And we believe this is due to an underestimation of this method. That is because this method basically accounts for the increasing weight created by the calcium carbonates, but also water is created in this process. You have to account for that. And in this process, it's very complicated because this water is converted into vapor, which is difficult to measure. However, we did want to verify that carbonation was happening, and for that we did thermogrammetric analysis, or TGA, which basically accounts or calculates the amount of calcium carbonate in the material, and with that we can calculate the CO2 uptake in these materials. And because this was just a verification, we did it on the samples exposed to 25% CO2 alone. Here we have these results, and as you can see, we have the weight of the sample as a function of the increase in temperature. So this test, what it does is basically takes the sample to high temperatures and records the weight loss over those temperatures. And if you know the range of temperatures where each compound decomposes, you can calculate the weight loss in that range, and that corresponds to the amount of that compound that you have in your sample. So calcium carbonate decomposes in temperatures higher to 550 Celsius. Therefore, the weight loss in that region is due to the amount of calcium carbonates that we have. So here we can see the red lines are the samples that are exposed, and we look at the difference between those two. We can actually see that nanomodification enhanced the CO2 uptake of the samples exposed by 32.7%. So The trend is clear in all of the tests that we did and all of the methods that we used to measure CO2 uptake. Nanomodification does enhance this phenomenon. However, why is this happening? So we previously knew that porosity is reduced when you add titanium dioxide nanoparticles. Therefore, this would induce a reduction of the CO2 uptake because we're reducing the diffusion of CO2 into the matrix. Therefore, our results seem a little counterintuitive. However, from a previous study that we did, we saw that this may be due to the reduction of the crystal size of the pH, making it more reactive. But is there any other mechanism affecting this uptake? And for that, we decided to look at the pore surface area of our materials. And to look at that, we did some 3D X-ray microscans of the samples that were not exposed. So we had nanomodified samples and not nanomodified samples. And what we found is that, yeah, porosity is reduced when you add titanium dioxide nanomodification, but pore surface area is actually increased in the samples that were nanomodified. So this means that this may be one of the causes that this acceleration is going on. As we have more surface area, we have more surface available for the CO2 to react with the hydration products in the solid matrix. And this is just kind of an illustration of what I want to point out. Here we have on the top an example of a reference sample, and on the bottom of a nanomodified sample. And as you can see, even though we may have kind of the same amount of pore volume, we do have more surface in the one below. Therefore, we have more surface area for the CO2 to react with all of the solid matrix where the hydration products are, making it more reactive. And with all of this data, we decided to do an estimation of the CO2 uptake rate. So it is commonly known that carbonation depth is proportional to the square root of time. So our proposed formula is to calculate this CO2 uptake, the mass of CO2 that's uptaken, with this same proportion. And that coefficient right here would be the carbonation rate coefficient, which, as we've seen from our results, it's affected by the nanomodification and CO2 concentration. So what we did is we took the data from our results to estimate this parameter, this coefficient. We used the least square method to estimate one value of this coefficient for each condition that we had. So we had three initial CO2 concentrations, 100%, 50%, and 25%, and two different percentages of titanium dioxide, 1% and 0%. And these are the results. And as you can see, when you are increasing the CO2 concentration, carbonation rate coefficient is bigger, as well as when you're increasing the titanium dioxide addition. Then we calculated the amount of CO2 uptake with this formula right here, with that new carbonation rate coefficient that we estimated. And you can see in this graph on the left that we have this estimation of the CO2 uptake that we calculated with our new formula, and on the x-axis, the actual CO2 uptake that we measure in the samples. And you can see that we have a pretty good estimation of that with this formula. So with this, we can see that using this 1% titanium dioxide nanomodification, we have an increase of this coefficient, and furthermore, this increase is higher for the lower CO2 concentration. As you can see here, the increase in the red part when we are exposing it to lower CO2 concentration, we have an increase of 39, almost 40% of the carbonation rate when you're nanomodifying the sample versus when you're exposing it to 100% CO2, which is just a 7%. So as some conclusions or takeaways from this study, we did see that CO2 uptake rate was enhanced when we use titanium dioxide nanoparticles for all CO2 concentrations. However, this effectiveness of our nanoparticles is higher when you're exposing it to lower CO2 concentrations. And we think that one of the reasons this may happen is because of the increase of the pore surface area when you're adding these nanoparticles. And just as a final remark as well, these results have been published last year, so if you want to take a look at that paper, you can take a picture of this or scan the code. And these are the references that I use. And that's all. Thank you so much.